This is part 2 of a review of limits and continuity. If you haven't seen part 1, you can click the link that will appear in the upper right hand corner or find the link in the description. In this video, we will focus on finding limits intuitively. In other words, we will be using our imagination. On number 7, the little negative sign right here means from the left. So we need to find the limit as x approaches negative 3 from the left of x plus 3 divided by the absolute value of x plus 3. I want to convince you that this limit is either going to be 1 or negative 1. For example, imagine that x equals 2. Then we would have 2 plus 3 over the absolute value of 2 plus 3. That's going to be 5 over the absolute value of 5, which is 5. And guess what? We get positive 1. Kabam! On the other hand, imagine that x equals negative 5. In that case, we have negative 5 plus 3 divided by the absolute value of negative 5 plus 3. And in the numerator, we have negative 2, while in the denominator, we have the absolute value of negative 2. Well, that's going to be negative 2 divided by positive 2, which turns out to be negative 1. Kabam! These are the only two possibilities. The denominator will be positive no matter what because of the absolute value. So if the numerator is also positive, that's when you get a positive 1. On the other hand, if the numerator turns out to be negative, then you're going to get a negative 1. So the only question is, as x approaches negative 3 from the left, is the numerator going to be positive or negative? As we approach negative 3 from the left, the values are going to be a little bit less than negative 3. So think about values like negative 3.01. Negative 3.01 is a little bit to the left of negative 3. So a little bit to the left of negative 3, I have negative 3.01 plus 3 divided by the absolute value of negative 3.01 plus 3. This is either going to be 1 or negative 1. And all that matters is the numerator going to be negative or positive? Well, negative 3.01 plus 3 is a negative number because the negative value is a little bit bigger in absolute value than the 3. So we have a negative divided by a positive since the absolute value is always positive. So we are going to get a value of negative 1 as we approach negative 3 from the left. All that work I was just showing you really would do in your head. That's why I'm calling this limits intuitively. We're using our imagination. So there's your answer. Number 8. Find the limit of this expression as x approaches negative infinity. When x approaches positive or negative infinity, we can often find the limit by thinking about what matters most. As x approaches negative infinity or positive infinity, some terms grow faster than others. So this term that has the x squared in it will grow much faster than the x term. So as we get closer and closer to negative infinity, the x term is not going to matter. Similarly, in the denominator, this constant is going nowhere, just stays negative 3, as the x takes off towards negative infinity. So this negative 3 is not going to matter. Again, this only works when x approaches infinity or negative infinity. But the limit of the original expression will equal the limit of this new expression where we only consider the terms that matter the most. This radical expression can now be simplified, but first I have to convince you that something you think you know is actually wrong. What do you think the square root of x squared is? Many of you were just saying x just now. the square root of x squared is x, because the square root and the exponent cancel each other out and you have x. That is not true. The square root of x squared is actually the absolute value of x. Now think about it. Imagine that x is, let's say, -2. If I take the square root of -2 squared, is the square root going to cancel out the 2 and leave me with a -2 the way you thought at first? No, it's not. Because what's really going to happen is I will square the -2 and get a +4. Oh, didn't mean to change colors there. I'm going to get a +4, and then I'm going to take the square root of that 4 and end up with a +2. So by squaring it and then taking the square root, I've now turned a -2 into a +2. What turns a -2 into a +2? That's right, absolute value. So when you square something and take the square root, that is the same as the absolute value of that thing. I'm mentioning this now because we have the square root of x squared. So as we simplify, the square root of 9 is 3, but the square root of x squared is the absolute value of x. So I have 3 times the absolute value of x divided by x. The purple part of this, as we saw on the previous problem, is either going to equal -1 or +1. Including the 3 in there, this limit will either be 3 times -1 or 3 times +1. In other words, -3 or +3. But as x approaches -infinity, will this expression approach +1 or -1? I'm talking about the purple part. The numerator is always positive because of the absolute value. Will the denominator be positive or negative? Well, x is approaching -infinity. So we're going to have a positive divided by a negative, which makes the expression negative. So we're in the situation where we have 3 times -1. So the limit is -3. Kabam! Number 9. Find the limit of this expression as x approaches 0 from the right. First, let me show you how you would do this for the AP exam. Kabam! That's it. The answer is 0. Now, let me go back and try to convince you that this is true. Here's the first thing that was going on in my head. I know that the function y equals natural log x looks like this. This is a graph that you should have memorized. So, what happens to natural log x as x approaches 0 from the right? Well, 0 is the y-axis. As we approach 0 from the right, the natural log x is just going down, down, down. In other words, it is approaching -infinity. So this natural log x part is approaching -infinity. Meanwhile, as x approaches 0, this term right here is approaching 0. So we are left with -2 divided by -infinity. If you take a constant and you divide it by something that's getting bigger and bigger in absolute value, the result is going to get closer and closer to 0. All that is in your head. We are finding limits intuitively. So you just put the limit equals 0. Number 10. What is the limit as x approaches infinity of sine of x over e to the x power? First, I will ask myself, what happens to the value of x over e to the x as x approaches infinity? I'll worry about the sine part later. And to answer this question, I'm going to use something called FEPL. FEPL is a made-up acronym that you will not find in a textbook, so please don't write it anywhere on your AP exam. But FEPL stands for factorials, exponents, polynomials, and logarithms. FEPL reminds us which types of functions grow fastest and which grow slowest as x approaches infinity or negative infinity. So in this case, we have an x in the numerator and e to the x power in the denominator. X is a very, very simple polynomial. Of course, e to the x is an exponential function. FEPL reminds us that polynomials grow slower than exponential functions. So as x approaches infinity, the numerator is growing slower than the denominator. Therefore, the denominator is getting bigger and bigger compared to the numerator. Therefore, the overall value of the fraction is getting smaller and smaller and smaller. In other words, it is approaching 0. FEPL tells us that the value of the fraction on the inside is approaching 0 as x approaches infinity. So the limit of the sign of this fraction as x approaches infinity will equal the limit of the sign of 0 as x approaches infinity. But we know that the sign of 0 is 0. So the limit as x approaches infinity is 0. So that's it. You really could have done all of this in your head and just put 0 for the answer, like we did on number 9. Number 11. The function h has a removable discontinuity at x equals 4 and a non-removable discontinuity at x equals -1. For part A, write a possible equation for function h. Well, when they say that function h has a removable discontinuity, they are talking about a hole. And you are going to get a hole at x equals 4 if we have two factors of x minus 4 that cancel each other out. So if we have an x minus 4 in the numerator and the denominator, that's how you get a hole at x equals 4. We have a non-removable discontinuity at x equals 1. That means that there's an asymptote at x equals -1. That will happen if we have a factor of x plus 1 in the denominator with nothing to cancel it out in the numerator. So right here, this is a possible function h of x that satisfies both of these conditions. So we just decided that our function will have an asymptote at x equals -1 and a hole at x equals 4. This is not what this function looks like, but I've drawn here a function that has a vertical asymptote at x equals -1 and a hole at 4. So we can use this picture to answer parts of B and C. Does the limit as x approaches -1 exist? Well, no, it can't exist because there's an asymptote at -1. So, no. If so, what is it? That does not apply. NA. Does the limit as x approaches 4 exist? Yes, it does. We know that there is a hole at x equals 4. So the limit as we approach 4 from the left is going to be the same as the limit as we approach 4 from the right. And if we approach the same value from the left and the right, the limit does exist. Whenever it's a hole, the limit does exist. If so, what is it? Well, here's where we have to use our function. Canceling out the x minus 4's will not change the limit. So the limit as x approaches 4 of h of x will equal the limit as x approaches 4 of 1 over x plus 1, the surviving part after we cancel out the x minus 4's. But this can be evaluated by direct substitution. This will be 1 over 4 plus 1, which is 1/5. Last one. Give the x-coordinate of all the points of discontinuity on f of x equals secant 2x on the interval from 0 to 2 pi. Indicate whether each point of discontinuity is removable or non-removable. Secant of 2x is the reciprocal of the cosine of 2x. So f of x really equals 1 over cosine 2x. This will have some discontinuities because you will get a discontinuity anytime you end up dividing by 0. And cosine of 2x does equal 0 from time to time. So our job is to find what values of x will cause cosine 2x to equal 0, which therefore will give us a discontinuity. By the way, any discontinuities that we find will be non-removable, because when you're dividing by 0, that's a vertical asymptote. So the question is, where does the cosine of 2x equal 0? Let's start by solving for 2x. Where does cosine equal 0? Cosine equals 0 here and here, because cosine is the x value on the unit circle. So that means that cosine will equal 0 when 2x is equal to pi over 2. All right, that's the one way up at the top, or 3 pi over 2. That's the one down here at the bottom. Now, why did I leave these so spaced out? That's because we have ourselves a periodic function. We can go around and around the unit circle and pick up more and more values. There are infinitely many values that will cause cosine to equal 0. So there can be more than one that will end up in the interval between 0 and 2 pi. We can't just go with the usual pi over 2 and 3 pi over 2 because we haven't divided by 2 yet. And dividing by 2 makes everything smaller, which means that more values may fit. So how will we get the additional values? The answer is by adding 2 pi. If you add 2 pi, you go all the way around the unit circle and get another solution. 2 pi is the same thing as 4 pi over 2. I'm thinking of it this way, so I will have like denominators. So if I take pi over 2 and I add 2 pi, so in other words, pi over 2 plus 4 pi over 2, that's going to be 5 pi over 2. So that's going to be another solution. Similarly, if I add 2 pi to 3 pi over 2, I will get another solution. 3 pi over 2 plus 4 pi over 2 is 7 pi over 2. So because I don't know how many solutions will fit, I'm going to find one more solution just in case. I can always throw out the ones that land outside the interval later. So I'm going to add 2 pi again to get another pair of solutions. So 5 pi over 2 plus 4 pi over 2 is going to be 9 pi over 2. 7 pi over 2 plus 4 pi over 2 is 11 pi over 2. So all of these are solutions. It's just a matter of which ones will fit. Next, we need to divide everything by 2 in order to get x by itself. So x will equal, pi over 2 divided by 2 is pi over 4. So all of these values are going to end up with a 4 in the denominator. Now we just have to throw out the values that are bigger than 2 pi. 9 pi over 4 and 11 pi over 4 are both bigger than 2 pi, so they are outside the interval. These are the x-coordinates of the discontinuities between 0 and 2 pi, and they are all non-removable.